Let me see if I can. Yeah, perfect. All right. So, hey everyone. It is an exceptional pleasure to be speaking in person for the first time since 2019. It feels a bit surreal, I must admit. My name is Petr Veličković. I am a staff research scientist at DeepMind and an affiliated lecturer at Cambridge. And today I will be talking to you about one of the things that I have been most passionate about over the past 4 or 5 years of my work in AI research. Specifically, I will be talking to you about how can we do deep learning on graph structured data. And specifically, I will try to do it in a way that convinces you that in reality, everybody should be doing deep learning on graph structured data. So let's see if I manage, right? So, why do I think representation learning on graphs is important? Well, first of all, this is because graphs are literally everywhere. They are all around us. Just look around you. Nature, social sciences, biology, chemistry, they are literally everywhere. If you look at, for example, the standard unit of reasoning in chemistry, the molecule, and you'll see very soon why I chose this specific molecule, you can think of it as basically an interconnected structure of atoms which are connected together by chemical bonds. So this very nicely fits in the framework of graphs. Then many human constructed systems such as transportation networks, here you have the tube map of London, is very easily represented in a graph structured form once again. You have nodes that are like train stations interconnected by tube lines. Then another human construct, the social network, here you have the friendship graph visualized for Facebook from some years ago, is also very nicely represented as a graph structure. Nodes can correspond to people and the links can correspond to the friendship connections that they make. And even as you dive deep into the human brain and you look at the connectomic structure of the neurons in the human brain, you can see that actually it very nicely maps to an interconnected graph structure of neurons. So our deepest ways in which humans do reasoning is very likely to be graph structured because in principle the way that signals are transmitted in our brain is following a certain kind of graph structure. And actually, if you look at it from a more holistic point of view, you can realize that graphs are in many ways the main modality of data we receive from nature. Like sure, deep learning has had lots of successes on images, on sequences and so on, but when does nature ever actually give us an image? When does nature ever actually give us a sequence? That's actually super rare. If you look at the way in which the data appears to us when we first observe it, it is very often observed in the form of some kind of a graph or geometric structure. And how we produce an image is how we project it into a particular 2D plane that we care about for this particular problem. So, and because it also appears to be underlying some of our cognitive processes, graph representation learning is likely to be very critical on the path to artificial general intelligence. That is, I find it very unlikely that we'll be able to achieve AGI or anything close to AGI without having a firm grasp of how to represent data on graphs. Okay. Now, it has taken some time, but the research community has caught on to this point, and if you look at statistics, and here I show statistics from the ICLR conference, which is very convenient because they show all of the papers submitted to the conference, including the rejected ones, you can see that graph neural networks are actually a super powerful and popular keyword. At last year's ICLR, they were the 4th most popular keyword behind generic terms like deep learning, RL, and representation learning. And if you want to find Graphnets, you'll find them way down there over here. And also, besides being a very strong topic in terms of representation, it's also very quickly growing. This graph here shows the delta of how more a keyword has been used at an ICLR paper compared to the previous year. And once again, graph neural networks are the fastest growing trend. And as I said, last time I had a chance to speak somewhere in person was 2019 when the NeurIPS conference last took place physically. And back then we organized a workshop on graph representation learning, which was in person. And actually we had 1,300 people signed up to attend, which was a pretty big deal. We were the 2nd largest workshop after deep reinforcement learning. And in many ways, and I hope I'll illustrate very specific examples, graph representation learning is currently experiencing its ImageNet moment where there's a lot of emerging applications, there's a lot of people coming into the field from all kinds of backgrounds, and basically if you want to get in on the action, now is the right time. So, the workhorse behind all of these successes in graph representation learning is usually the graph neural network, or GNN for short. And I won't, because this is a high-level talk, I won't dive into a lot of details on how graph neural networks operate. But basically, you probably know that graphs can be represented as a set of nodes connected between them by a set of edges. And if you want to compute interesting features on a graph, you could expect that you have some features in every one of your nodes. So xb would be the vector features in node B. And you want your graph neural network to meaningfully compute some higher level representations in that particular node, much like a convolutional net would for pixels in an image. And the way in which this would be done, if you think about it, is usually done in just a way that pretty much straightforwardly generalizes a convnet. You need to take into account all the neighbors of a particular node, and your graph neural network, G, takes into account the features of the node and the features of all the nodes that are adjacent to it, and somehow, as a function over that entire set of neighbors, produces an updated representation. You can then run this across all the neighborhoods in your graph in parallel, and that gives you one layer. And then, in the spirit of deep learning, you can put activation functions, stack more layers, blah, blah, blah. So once you have a GNN like this, imagine you have a graph structured input that has features in your nodes. So xi would be the vector of features inside the node I, and you have some edges between them specified as an adjacency matrix. You run your graph neural network, and as a result, usually it leaves the graph structure alone, although there are some interesting works that also change the graph structure. And you get, as a result, updated features, now H to represent hidden or latent in each one of the nodes. And what can you then do with these features? You can, for example, classify individual nodes by just learning a classifier based on the H's. You can also classify entire graphs, but you have to be careful that the prediction doesn't depend on the order in which you feed the nodes to the classifier. So usually what you do is you perform some kind of aggregation over all the H's for all the nodes. So this will typically be like a sum or average or something like that. So you compute this aggregation over all the vertices, and then you pass those to your graph classifier to classify entire graphs. And one thing that's pretty interesting and sort of unique to graphs is that there's also a third modality, which is the link, so the edge between two nodes. So you can classify interesting properties of these links, or you can even predict whether or not a link exists, in which case this task is called link prediction. And now you have a classifier which could take into account the features of node I, the features of node J, any edge features you might have between them, and so on. You can use that to also do interesting tasks. So I've showed you this as kind of a foundation for all the principal tasks we can do if we have access to a GNN, and I'll show you what are the cool things you can actually do with them. So, as I mentioned, GNNs have already seen some pretty interesting applications in both science and industry, because people are slowly starting to realize that the modality of data they actually have is graphs and not something else. So, let's start with my favorite example, the example of computational chemistry. So as I mentioned at the very beginning, molecules are graphs. It's a very natural way to represent molecules, where you look at different atoms as nodes in a graph, and the different chemical bonds as edges in a graph. And you can put, as I said, node or edge features, such as what's the atom type, is it a carbon, hydrogen, nitrogen, and the bond features could be what's the bond type, is it a single bond, double bond, is the atom in a ring, so on and so forth. So here I have, for example, I think this is the molecule of paracetamol. I hope I'm not wrong. Now, as I mentioned, one of the principal tasks we can do once we have a graph structured input like this is graph classification, right? So we can take this graph corresponding to a molecule, pipe it through a GNN, and then predict some interesting property about the molecule. Now, what's a very interesting thing to do with molecules these days? Well, you might want to see which molecule could be a useful drug. So you can actually build up a data set of known molecules for which you know how they affect certain bacteria, for example, Escherichia coli. So you basically have yourself a binary classification task. I give you a molecule graph, predict whether or not it will inhibit this particular bacterium. And you can basically train a GNN on this particular data set, and the exact GNN that the authors of this paper used is really very close to the basic model that I showed you a few slides ago. And what's really cool is that when you train this GNN to predict whether or not a molecule is a potent drug, you can then apply that GNN to any molecule you want, right? Because it's a binary classifier, it will output some probability, like how much do I believe that this molecule is a potent drug. And you can basically take a large data set of known candidate drugs. The reason why you'd start with candidate drugs is because these molecules have already went through some kind of clinical trials, so you don't have to worry about repeating all that process all over again. And your GNN will give some probabilities for all those candidate drug molecules you have in your data set. And you take the top 100 or so candidates and you send them to chemists. And then chemists can thoroughly investigate, do these top 100 make any sense? And it turns out that after they've done some filtering, they've discovered this exact molecule I've shown you in the first slide, called halicin, which previously nobody studied in the context of antibiotics. Now, I'm not a chemist, but from what I understand, antibiotics are typically not expected to have a structure like this. And in fact, halicin was previously clinically studied for a completely unrelated thing, for diabetes. But it turned out that it's a super, super potent antibiotic, and because it has this unusual structure, people haven't used it as an antibiotic before, which means all of those antibiotic-resistant bacteria that evolved over the years are not resistant to this guy. So it's a super potent antibiotic against even bacteria that have developed antibiotic resistance. And of course, this is a pretty impressive find, so when you get something like this, you want to get it published, and you get it published in a pretty top-tier journal in chemistry. And afterwards, this thing gets picked up by all sorts of venues, right? Nature, Financial Times, BBC, whatever. You might remember this. This happened right before the coronavirus pandemic. There were a lot of titles in the press about scientists discovering powerful antibiotics using AI. So it was done by this fantastic team of researchers at MIT. And well, now you can basically know that this AI in question was really just a graph neural network that was trained to predict antibiotic properties. So that was the first application I wanted to show you, and virtual drug screening, a very important and very emerging thread, because we know about this one example. Can you think about how many other examples we might be missing, right? Then, as I mentioned, graphs arise a lot in industrial contexts. So social networks are very nicely represented as graphs. Product networks are nicely represented as graphs. And believe it or not, the industry has caught up to that. And now most of the major industry players are using some kind of graph neural network to power stuff that they serve to you. So, for example, Pinterest was the first one to catch on to it. Their PinSage model recommends content for you on Pinterest. Amazon uses the P-Companion model to recommend which products you should buy after you bought a particular product. And Uber Eats is using graph neural networks to recommend which food you should eat next based on all the foods that you've eaten before that. Okay. And one that I'm particularly also excited about, because it's the first time GNNs actually appeared in Nature proper, is this recent paper from Google AI, which used graph neural networks to develop new chips. Turns out designing and putting different pieces of electronic on a chip is a pretty complicated task, and human design heuristics haven't necessarily been optimal. So looking at the chip more as a graph rather than as a grid, which is how people previously looked at it, turned out to be a pretty powerful way of looking at it. And it went as far as Google AI is currently using this reinforcement learning graph neural network for chip design to design its latest generation of machine learning chips, the TPU v5. So in a way, these kinds of findings are a way in which graph neural networks are affecting anybody who's going to be doing machine learning in the near future as hardware continues to evolve. Now, I am a research scientist at DeepMind, and I haven't really mentioned any contributions from DeepMind yet, but as you might expect, DeepMind has not strayed away from the fun either. So here are some impactful applications that came from my company. First, one thing that is actually quite interesting is that when you look at physics and interactions between particles and forces between them, it feels a lot like a graph structure, right? In fact, it turns out graph structures are a pretty neat way to explain forces between particles and their evolution. And in this particular paper, the team from DeepMind was able to use graph neural networks to predict the future motion of particles in glass. And it turns out that this was actually a really tricky material to model, because unlike liquids or supercooled liquids or crystals that stay stationary, glass has very tiny movements over very long time scales, and it's really tricky to model exactly how they worked. And using a GNN, they've been able to get a better explanation of their trajectories, and they managed to publish this in Nature Physics. Okay. Then one very important application industrially is a combinatorial optimization. So very often if you're dealing with supply chains or these kinds of problems, you have to figure out how to optimally move equipment around and so on. This usually can be cast as a kind of mixed integer program. So it's a problem that you have to solve based on a particular set of constraints. And the team at DeepMind and Google Research realized that you can actually cast this problem, the combinatorial optimization problem, as a graph, where your nodes are the variables that you have to optimize, and also the nodes are the constraints that those variables have to satisfy, and you connect a variable to a constraint if it features inside that constraint with a particular coefficient, and then you let your graph neural network try to figure out what's the best way to derive solutions. Okay? So in this way, they've been able to expedite the solving process of some standard mixed integer programs that Google has to solve on a daily basis. And one which I'm going to be talking to you about in more detail right now is also the work on using GNNs for travel time prediction. So this is a paper that I've also been involved in. You can see me here as one of the authors. And we looked at the problem of predicting the travel time when you have a particular route. Now, it should be fairly clear that transportation maps can also be represented as graphs. So you have different parts of the road and the road that connects them. And a very common task you might want to ask yourself is, how fast can I travel from point A to point B? This is a task that very often systems like Google Maps need to solve. And I was one of the people who worked on deploying graph neural networks into the system that predicts these travel times, and this is now actually served worldwide, and in some cities has improved the travel time estimates by up to 50%. So, how have we enabled scalable traffic predictions in Google Maps with graph neural networks? Well, as I mentioned, you can think of traffic maps as a very natural graph structure. So here might be a typical picture that you see from Google Maps, and here might be one way in which you can decompose it into a graph structure. So nodes could be intersections, and edges could be roads connecting them. And one very critical service that Google Maps provides for you is the travel time estimation, right? Or ETA prediction. So given a particular start point, end point, and a route, what's the expected travel time along that particular route? And this is not just important for us users when we ask Google Maps to tell us how to get somewhere. Turns out there's a lot of enterprises like ride sharing and delivery companies that rely on Google Maps' API to tell their customers when is their food going to arrive, when is their cab going to arrive, and so on and so forth. So in a way, this actually impacts a lot of users on a daily basis. And there's some interesting node features you can put, like what's the length of the road, what are the current speeds, what have been historical speeds at this time of day, and so on and so forth. And Google Maps has gathered lots of anonymized, crowdsourced, real-time historical data. And there's a lot of challenges with using this data because, it's collected using the app, so it's not as reliable as, say, physical speed sensors. And sometimes to predict the travel time, you need to anticipate an event that only happens in the future, right? There's some rush hour that's brewing, but the current traffic conditions don't necessarily tell you that it's coming. So the way in which DeepMind has attacked this problem is by partitioning the road network into these connected components called supersegments. And the way they're sampled is roughly based on traffic density. And then once you have a supersegment, you can run a graph neural network over the graph corresponding to it to estimate what's the travel time along this segment. So it corresponds nicely to a graph regression problem or graph classification problem, as we discussed before. And once you have a system like this, it nicely fits into the whole pipeline of how Google Maps serves you routes. So the user asks for A and B, and then the Pathfinder gives a bunch of candidate routes for our neural network to score. And then the neural network predicts the travel time for every one of those routes, and they get ranked. And that ranking then gets surfaced to you in the app if you're using the Google Maps app, or also surfaced to the API if you're an enterprise that uses Google Maps. And this has actually by now already been deployed worldwide, so no matter where in the world you are, if you ask Google Maps for the time it takes to travel from A to B, it is going to incur a call to our graph neural network, which is served in production. And at the time of deployment, we have deployed it in several cities around the world, and in some of them it has caused a significant improvement to the number of negative outcomes, that is, when our system was off by more than a certain threshold of, say, 10 minutes or so. And in some cities like Sydney or Taichung, the improvement was over 40% relative reduction in negative outcomes. So in a way, this is a very clear example of a graph neural network that impacts billions of people's lives on a daily basis, because that's roughly how many queries get served. Okay, so hopefully what I've said so far is a nice kind of high-level overview of why this is an interesting area and that you should potentially also get in on the action. Now I will tell you a bit about some interesting resources for how to get in on the action, and I'll also tell you about one very interesting problem where even very trivial solutions can lead to a research paper. So basically it's an area where you can quickly get to grips with what the problem is and also propose some interesting solutions off the bat. So one thing that I mentioned before is that Graphnets are currently experiencing their ImageNet moment, but unlike ConvNets at the time when ImageNet was a big deal, we have a slightly better starting point because now we have a lot of different frameworks, PyTorch, TensorFlow, JAX, which all support very interesting numerical computations, and also for every single one of them we have libraries that are custom built for graph neural networks. So you don't have to actually understand all of the internals of how they work, you can just use one of these libraries and use Graphnets as a black box, basically part of your neural network architecture. So if you're using PyTorch, you can use PyTorch Geometric or DGL. If you're using TensorFlow, you can use Spectral or DeepMind's Graphnets library. And if you're using JAX, which I would highly recommend, you should use DeepMind's Giraffe library, which we've custom built for Graphnets in JAX. And also, another thing, you know, you cannot have good machine learning without good data, unfortunately. And it turns out that also in that regard we have a slightly better starting point than say ImageNet models might have had, where you basically had the choice of basically MNIST, which was a sanity check, and then maybe CIFAR and not much beyond that. Actually, you know, people are realizing the importance of having good graph data sets, and they are very actively working on a very rich ecosystem of those data sets. So Stanford's Open Graph Benchmark is a pretty amazing resource. Benchmarking graph neural networks from the team at Singapore is also very good. And PyTorch Geometric also comes with a lot of very interesting data sets pre-packed. And if you're interested specifically in graph classification, you might find the TU data sets to be quite interesting. And beyond, you know, just saying these are the libraries, these are the data sets, I also have left recently and over the months several resources lying around for getting started with these models. So if you're interested in just, you know, a curated list of blog posts, books, courses, basically any modality of learning that you prefer, I some time ago compiled a Twitter thread which lists all of these things. And that can be a pretty good starting point if you want to get more involved in these things. But when you feel ready to like start implementing these models and you want to see what an implementation might look like, one of my compatriots, Alex Agordic, who recently got a job at DeepMind as a research engineer, has put up on his Git repository a very interesting implementation of graph attention networks, which was a model we proposed some years ago at iClear. And in my opinion, it is arguably the most gentle introduction to GraphNet implementation. So if you've never seen a GraphNet code before, it comes not just with implementation, but with very nice step-by-step Python notebooks so you can visualize literally every step of the way. So it's a very nice way to kind of visually get introduced to what these models are actually doing. Okay. So I hope these resources are useful. We can obviously discuss them after the talk as well if you're interested. Now I want to tell you a little bit about a very interesting problem which should hopefully be simple enough that we can you know, dive into it very easily off the bat. And that is the problem of graph isomorphism testing. If you haven't heard about it before, that's totally fine. I will explain what it is in a second. So one thing that, you know, we're asking ourselves, because Graphnets are permeating every single aspect of, you know, science and industry, is, you know, they're so powerful for real world data, but how powerful are they actually? Like, can we theoretically reason about how powerful they are? Are there things that they cannot do? Yes, there are things that they cannot do. P is not equal to MP, and, well, probably. And Graphnets are in P. So until we resolve that question, there are certainly some problems that Graphnets cannot solve perfectly. And one canonical example that we use for this is the task of deciding graph isomorphism. And I won't get into the maths of it. I'll just say, can I use my GNN to put two different features to two graphs that are not the same? Okay, non-isomorphic graphs. Because if my GraphNet doesn't put different features on these two graphs, any kind of classification task I want to do on them is hopeless, right? I have to put them in exactly the same class, even if they're classified differently. So if I cannot put them different vectors, nothing else can be any easier, right? So the way in which we typically assess the power of GNNs is by which graphs are they able to distinguish, like put different features on these two. Okay, and one very popular and very old approach to doing graph isomorphism testing came from two Soviet mathematicians, Lehmann and Weisfeller. And it's a very simple but very powerful way of distinguishing, and you'll see how powerful it is in a few slides' time. You just pass random hashes of sums along the edges of the graph and iterate until there's no change. And based on whether these histograms of hashes look the same, you say possibly isomorphic or non-isomorphic. And that's it. I'll show you in a second. So let's run it on a graph. So we have a graph like this. Initially, I put a feature in every node like that, and now I pass random hashes over my edges. What's going to happen after one iteration? Well, you have 3 blue nodes with 2 blue neighbors. They'll get a particular color, green. And you have 2 blue nodes with 3 blue neighbors, and they will get a different color, yellow. So what do you think might happen in the next step? How many different cases do we have? It turns out that you have 3 cases. Yellow nodes with 2 green neighbors, they'll get some color. You have green nodes with 1 yellow and 1 green neighbor, they'll get a different color. And you have green nodes with 2 yellow neighbors, they'll get a new color invented for them. And it turns out when you iterate this process one more time, nothing changes. So that's it. That's the histogram for this particular graph. And as you would expect, if I give you a graph that's isomorphic to the original graph, you can stare at it for a bit and see that these 2 graphs are actually exactly the same. You'll get exactly the same histogram, so everything is great, right? Obviously, there are many cases that this test cannot distinguish. One very common example is it's really terrible at detecting cycles. So if I give you a 6 cycle and 2 triangles, disconnected triangles, the Weisfeiler test has no way of saying whether these 2 are different. It says they're possibly isomorphic. So, okay, there are some clear failure cases and they seem fairly straightforward. So what does this have to do with GNNs? Well, it turns out that if your features are discrete, one-hot features, GNNs can never be more powerful than this test that I just described you. In fact, there's a very nice proof that says if you prime your GNN so that it computes sums over the neighborhoods, then it's able to capture as much properties of the neighborhood as the test would, and it cannot do anything else. And based on this, they proposed this graph isomorphism network, which is just one simple example that follows this sum aggregation. Okay, so this sounds particularly dire, right? There are some very simple cases of graphs that this GNN cannot distinguish. But basically, if we look at what are the failure cases, we can design different versions of GNNs that might be in a better place to tell them apart. So, and this is, I must say, it's a very active area. There's many open problems, but let me show you just how close we are to an open problem at this particular point. So, as I said, we cannot detect closed triangles, so we cannot tell apart this 2-triangle graph to this cycle graph. And the reason why is because when you run a graph neural network, these are the nodes that it sees in its k-hop receptive field. You see, the receptive field for these 2 nodes looks exactly the same. So can you think of something very simple that we can do to make sure that these 2 receptive fields are different? Anything we can do to the input? Any thoughts?
Well, I mean, if you can figure out where the cycles are, you can just pass them in separately.
Okay, so you basically put a feature in that tells you what's the cycle, right? You can do something even simpler than that. You can literally put a random number in every single node. And now suddenly my receptive fields look different, right? So even something as simple as I put a random feature in every single node is enough to tell them apart. And it was also enough to get a high-ranked publication in the year of 2021. So this is like doing something as simple as put a random feature in every node is enough to get you a research paper in this area. Just to be clear on that. And and of course you have to theoretically prove it, but the idea is basically now a node can see itself k hops away, so you can tell that you're closing a cycle, right? So this is just one very simple example in a series of examples. As according to the suggestion we heard just now, you can literally even pre-compute subgraphs of interests and put them as features, right? And basically whenever you fix a failure case of the Weisfeiler test in this way, this gives you a class of higher order GNNs. And there's many interesting ways in which you can categorize them. They can either modify the features as we've done above, so put some different features in your graph that sort of do some computation that the Weisfeiler test doesn't have access to. Or you can modify the equation that the GraphNet is computing to somehow take into account the structure. Or which I find most exciting, you can actually modify the graph structure. You can put new nodes or new edges that sort of hint to the model what the structures might look like. And I've left around a few references if you'd like to take a look at how different groups go about solving this particular problem. But I hope, it's a very simple question, right? Can I get different features for these two graphs that are different? And even answers as simple as put a randomized feature in the node is publication worthy in the year 2021. So basically, it's something that anybody can get in on the action if you feel so inclined. And one interesting point that I'll leave you with before going to the closing part is I said that the proof of Graphnets being the same as Weisfeiler test is only when features are discrete, one hot. But what if the features are continuous? Like, it's very common when you have natural data that your features are going to be continuous, right? Well, it turns out that the proof of the sum being optimal falls apart in this case. I can easily construct neighborhoods that are like continuous, where taking the sum, taking the average, taking the max doesn't work, doesn't distinguish these two neighborhoods. And it turns out we went on and investigated this, and we published a paper at NeurIPS last year, which showed that, well, there doesn't seem to be a winner aggregation function, and we prove actually that there isn't one. If you have n neighbors, to be able to clearly tell apart the neighborhoods, you need at least n aggregators. And for those of you that are mathematically inclined, I would ask you to take a look at the proof in this paper. In my opinion, it's really cool. It uses the borsa coulomb theorem and basically spheres in n dimensions. And in our paper, we take this, this idea of having many aggregators and try to kind of combine the ones that are numerically stable, like mean, standard deviation, max, min, and maybe some scaling based on the degree. And this combination of 12 aggregators, so not n, but 12, seems to be powerful enough and stable enough in practice, but it's very much an open problem what a good basis of aggregators might be if you're interested also looking into that. Okay, so hopefully I've shown you that most of the data you're ever going to see is in reality a graph structured datum. And I've showed you how graph neural networks are a decent way of dealing with that kind of data and how they're already becoming impactful in a lot of areas, both industrially and scientifically. And I've showed you, if you're interested in like looking into the latest and greatest in GNN theory, that it's actually not that far-fetched compared to where we are right now in the state of the art. So now I'd just like to leave you with a few further resources if you want to listen to more targeted talks that just talk about what a GNN is, where is a GNN applied, basically a deep dive into some of the parts of this talk today. So if you haven't heard much about GNNs before and you would like to learn a bit more about them, some months ago at Cambridge I gave a Wednesday seminar talk at the Department of Computer Science, and I made the talk publicly available on YouTube. So if you want to listen to me talk about graph neural networks, just graph neural networks for 1 hour, and about the theory behind them and how to build them and so on and so forth, this is probably the talk I would recommend first. And if you want to know a lot more about where they're being applied, so not just drug screening and travel time estimation, but also how they're applied in social networks, how they're applied at the Large Hadron Collider, how they're applied at autonomous vehicles, and so on and so forth. I have a talk that I gave at EML 2 years ago, which deals specifically with that. So where are the interesting parts where graph neural networks have seen application? You can see me here talking next to Razvan Pashkanu, who was my moderator for this talk. And once again, the talk is available on YouTube if you'd like to listen to me talk for 1 hour just about applications. And that was actually my last slide. Thank you so much for listening. We'll be very happy to answer all your questions. And once again, thank you so much for coming out. I'm really happy to be giving a talk in person again. If for any reason you want to contact me offline, I'm very happy to discuss about all kinds of things related to graphs or otherwise. I've left my email here, and all of my social networks can be found on my website. Thank you very much.